Today we're going to take a look at what are called plane curves, plane meaning coordinate plane, and parametric equations. So we have a few things we want to take a look at: how to graph parametric equations by hand, how to graph them using technology. We'll use the graphing calculator today. And how to find a rectangular equation for a plane curve that's defined parametrically, how to use time as a parameter, and how to find parametric equations for curves that are defined by a rectangular equation. So when we say rectangular equations, we mean equations that are defined using rectangular coordinates, or more commonly x comma y coordinates. So what you guys are typically used to using for the xy plane. So what have you been doing mathematically, and how's that going to relate to what we talk about today? So what you guys have been working on for most of your math career have been relations. Remember, relations are collections of ordered pairs. So two variables are related to one another somehow, some way. We call any such collection a relation. You guys have mostly worked with relations that are functions, where every input has exactly one output. So the most common variable for input is x. The most common variable for output is y, but they don't have to be x and y. Those are just kind of become commonplace nowadays. So typically we define the output to be a function of x, and we have function notation for that. So x is the input, and when you input that, it outputs f at x, which could be y, right? Remember, if we know it's a function, we often use function notation instead of a y. But again, the idea is that x is the input and y is the output, or f at x is the output. And you guys have done a lot of work with this. You guys have worked with polynomial functions, rational functions, exponential functions, logarithmic functions, and trigonometric functions, just to name a few. So this is what you guys have spent most of your time working with. But recently, you've had some experience with relations that are not functions of x. So you guys briefly studied the conic sections. So circles are not functions of x. Neither are parabolas that open to the left or to the right, whose axis is horizontal. Neither are hyperbolas whose transverse axis is horizontal. So these aren't the only non-functions you've worked with, but they are the recent ones. Well, most of the time, if not all the time, you guys have represented these as either functions of x, if they were functions, or using some xy equation that wasn't a function of x. So for example, the circle centered at 0, 0 with a radius of 1, you would write, well, that's x squared plus y squared equals 1. That's not a function of x. You can't write that as one equation where y depends solely on x. You can write it where y squared depends solely on x, but not as y depending solely on x. So things that are not functions of x, we kind of have to use equations that involve x and y, and you can't really you can't isolate y using just one equation. So that's what I mean here when I say relations that are functions. You can always write them using one equation where y depends solely on x. So if you just know what x is, you plug it in, and then you get your one output y for that x value. And then, but relations that are not functions of x, you can't write them in exactly that manner. Now we have ways around it, but you cannot just have one equation where y is by itself with a coefficient of 1, an exponent of 1, and then you have one expression for x on the other side that defines y. Well, it turns out there's another method of defining relations, x, y, that you could use for either functions of x or non-functions of x, and that one method applies to both. And that method uses something called a parameter, which is essentially a third variable. We introduce a third variable to the situation, and you can think of it as kind of almost a temporary variable, because we use it to figure out what x and y are, and then we only plot the x, y. You'll see what I mean here in a sec, but we get this third variable called a parameter. And this way of defining a relation, it doesn't really care whether the relation's a function of x or not. It'll just kind of handle it all the same. So let's give this a try. So let's graph the following. Let's take a look at what we have here. We have the x variable is defined as t plus 1. Now t is going to be the parameter. T is that third variable that we're going to introduce. But then the y-coordinate is always defined as 2 times the parameter t. And we're going to let the parameter vary from negative infinity to infinity. In other words, t can be any real number. We're going to let the parameter be any real number. Now, as we're going to see, this is going to define some relation on the xy plane. Now, to get a feeling for what it defines, let's make a table, just like we did way back in pre-algebra and algebra 1, where we had an equation, we didn't really know what it was, so we made a table. So this table, however, it's going to have 3 columns. So we're going to need to know what the value of the parameter is, and then once we know that, we can then go figure out what x and y are. Now notice that the parameter can be any real number. Well, we can't pick every real number, so we're just going to pick some in numerical order to get a feel for what x and y are. We're going to look for a pattern. So what if we plug in, say, -3? So start with some negative values of the parameter. Well, if I plug -3 in for x, I get -2. If I plug it in for y, I get -6. So that one value of the parameter corresponds to the ordered pair, -2, -6. So let's go plot that. So -2, 1, 2, 3, 4, 5, 6 will be down here. What if I were to plug in -2? Well, then I'd get -1, -4. So I just get another coordinate, -1, 1, 2, 3, 4. What if I were to plug in, say, -1? Well, then I'd get 0. And then -2. So I'd get 0, -2. And I don't have to pick integers. I could pick something like, I could pick, let's see, oh, the other one I plotted wrong, didn't I? Oh, no, I didn't. Yeah, 0, 2, we're good. What if I were to plug in, say, -1/2? So if I plug that in for x, I get +1/2, and then I get -1. So that'd be like right there. So there's nothing stopping me from picking rational numbers or irrational numbers. If I really want to make things difficult for myself, I can. Because remember, t is allowed to be any real number. But eventually, the idea here, just like it was back in Algebra 1, was that we're looking for a pattern. And I notice these 4 points I plot all appear to be linear. So let's pick one more. What if I pick 2 for the parameter? So then I'd get 3, 4. So then I'd get 1, 2, 3, 1, 2, 3, 4. And sure enough, that does appear to be a linear relationship. So remember, t could have been any real number. So there would have been a whole bunch of other points that I could have plotted, but they all appear to fall on this line. And remember, I could keep picking values of t, so this probably goes forever in both directions. So it appears that this parametrically defined relation is a function of x. It appears to be linear. Now, how could I verify that? How do I know for certain? Well, it turns out you can just get rid of the parameter. So if x is t plus 1, then t is x minus 1. Just solve for t. And if y is 2 times t, then y would be 2 times x minus 1. So y would be 2x minus 2. That's a line. That's a first-degree linear polynomial. Goes through -2 with a slope of 2, and that is exactly what we have here. So now I know for certain that I was supposed to get a line. I can see it right here. So this would be rectangular. This would be a rectangular equation, because it just uses x's and y's, which are rectangular coordinates. So that would be the rectangular equation form of this parametric equation. So this is a parametric equation. Because it uses the parameter t. So it's not super difficult to graph a parametrically defined curve, and there's ways to speed it up, just like there's ways to speed up the other ones, and we'll talk about some of those. Now, this t, again, we call that the parameter. That's that third variable that both depend on. And the other thing that's important here is by introducing this parameter, if we evaluate the parametrically defined curve in numerical order, meaning notice that is what I did in the table. I did -3, then I picked a larger value of t, -2, then I picked a larger value of t, -1. So I let t get larger and larger and larger. And when I do that, what we get is we get an order or a direction at which the curve was traced out. So this curve was plotted in this direction. Put these little arrows to show that the curve was plotted in that direction. Now that direction is called its orientation. So parametrically defined curves have an orientation. So get this little vocab word here, orientation. Which is the direction they are traced out as the value of the parameter is increased. So whatever the direction that it was traced out or plotted out in, as t is increased, is its orientation. So that's pretty handy. If you ever want to model something where direction is important, you're trying to show the direction in which something moves maybe, then you definitely want to use a parametrically defined curve to do so, because that orientation comes with it. So quite handy. Well, what if we wanted to graph this using technology? So I'll show you how to do this on the graphing calculator. It's always nice to have another tool by which you could get a graph to verify things, check for the reasonableness of what you think is going on. So on your graphing calculator, on the scratchpad side, we don't really need to use the document side for anything. So on the scratchpad side, let's go ahead and choose graph, which is option B. And then it typically defaults to functions of x. You'll see that right here, function of x, but we don't want that. So hit menu. And then we want the third option, graph entry edit. So we're going to go menu, graph entry edit. And then we want the fourth option that says parametric. So we'll go down to parametric and choose option 4. And it's fairly self-explanatory. It's basically going to say, well, what do you want x to be? Well, we want x to be t plus 1. And then what do you want y to be? Well, we wanted that to be 2 times t. And then it's going to say, well, what values of t would you like to work with? Well, we want all real numbers, but that's a lot of numbers, and the calculator is not going to like that. So instead, let's just go pick a rather wide interval of t. So let's go like -20 to 20. So that's not all real numbers, I know, but it's still going to tell me whether my graph is correct or not. It's going to give me enough of the graph to compare with what I've done by hand. Now that t step, we're just going to leave that alone. You typically want that to be a small number, close to 0. Big can be bad. We'll talk more about that if we graph one of these later that's a little bit more intricate in its shape. So typically we'll just leave the t-step alone. Now if we hit enter, notice it graphs the exact same line that we graphed, which verifies that we knew what we were doing. We got the right points, plotted them, all is well. Notice it doesn't show the orientation though, so it has its limitations. That's one of the benefits to, believe it or not, this is one of those situations where older technology was actually a little bit better. So when graphing calculators were new, their processing speeds were slower. So it actually plotted the points so slowly you could watch the curve be traced out. So it actually did show the orientation because it would show the curve being traced out, but with these modern graphing calculators, it plots them so fast you can't see it. So it's got its limitations. It doesn't show the orientation when you hit enter and graph it, but that's okay. Okay, let's go graph another one. Let's do one more. So let's graph this one, a little bit more complicated. So let's graph x equals 3t squared and y equals 2t. So one of the things I want to point out is notice that 3t squared itself is a function of t. So if I plug in t, I get one and only one output, f at t, which we're calling x. And then this is a different function of t, so I'll call it g. So notice that x and y separately are defined as functions of t, and that's important. X and y need to be defined as functions of t. There should be only one output x and only one output y, so you can get your coordinate and plot it. So that'll be important here when we define parametric equations here in just a sec. This time, though, notice that t has endpoints. So t is defined on a closed interval, not an open interval, not the whole real number line, but just from -2 to 2. So let's make a quick chart. I'm just going to pick integers unless I have a reason not to. We'll see. So if I pick -2, which is the smallest value of t I'm allowed, I get 12, -4. So if I go plot that, 2, 4, 6, 8, 10, 12, 1, 2, 3, 4. That's a closed dot. -1 would be 3, -2. 3, -2. And then if I plug in 0, I get 0, 0, the origin. Then if I plug in 1, I'm going to get 3, 2. Ooh, I got some symmetry going on. So I have some symmetry about the x-axis, it appears. And then if I plug in 2, I get 12, 4. Oh yeah, so I've got some symmetry about the x-axis. I think I plotted that point in the wrong spot. Let's come over here. 1, 2, 3, 4. So that pattern, again, knowing I could have picked any number between -2 and 2, that pattern appears to be that the curve is going to trace out in this direction. So my orientation would be like this. And yes, you do put the arrows on the curve to show the audience the orientation. So it appears to be part of a parabola whose axis is horizontal. It's just part of a parabola, though. It's got endpoints, because t's not allowed to vary between -infinity and infinity. This thing's got endpoints. So it's only part of a parabola opening to the right. Now, how can I verify that that's correct? Well, we can eliminate the parameter. So y equals 2t, which means t is 1/2 y. So then I can plug that in for x. So x equals 3t squared. So x equals 3 1/2 y squared. So x would be 3/4 y squared. And hopefully you recognize that from your study of conics. That's basically this equation. Y minus 0 squared equals, what would that be? 4 times 1/3 x minus 0, if I did that right. So h is 0, k is 0, and then what I typically call distance a is 1/3, but I'm not sure how you guys defined parabolas when you did your conic sections. But this is the form I would usually use. But still, whatever form you used, you could take x equals 3/4 y squared and convert it over into the whatever graphing form you use for parabolas that have a horizontal axis. So that does make sense with what we're seeing in our picture. So I think we're good. So now that we've played around with this, I think we're ready to write a formal definition of what a parametric equation is and what a plane curve is. So here we go. So here's our definition. So we're going to let x be some function of t. We're going to let y be some function of t. Could be different, though, so that's why I'm going to call this one f and this one g, because they could be differently defined. F and G will have some common domain. We'll call that domain, some interval I. So there's some part of the real number line that is in both the domain of F and G, and those are the T values that we'll be allowed to plug in. So for example, back up here, that's what this was. That is the interval for which I'm allowed to plug into both the X and the Y's definition. So that's what I'm referring to down here. Then the set of all points x, y that we get from that relationship is called a plane curve, plane coming from coordinate plane. And then the x and y equations themselves are called parametric equations. So those two things together, those are parametric equations. And t is the parameter. And by the way, t doesn't have to be the parameter. It can be lots of different stuff. Another common one is theta for an angle. T is just the commonly used variable for a parameter. It's just like using x and y for equations. It's just the commonly used variables. T is a commonly used variable for a parameter. Now, parametric equations are quite useful when time is involved. That's kind of how we settled on t being commonly used for parameter. So if time is involved, and time's important to show because it shows like direction of movement or where something's at in a given moment of time, then parametric equations are quite useful. And then having time be the parameter is quite useful, as you'll see here in just a sec. So as an example of when time would be useful, we're going to see how projectile motion can be modeled by a set of parametric equations. So the setup is this. We don't want to get too deep into the physics of it, but the setup is this. You have a projectile that's going to be launched into the air. So we need some information first. Well, we're going to need to know what's its height at the moment it was launched. So I'm going to have the x-axis be the ground, and then this distance here would be h. That'd be the height that it was launched from. We also need to know the initial velocity. So how fast was it launched at, so when it was projected out of whatever it was, maybe it's a cannon shooting a cannonball. So what was the initial velocity of that cannonball? We need that. We're going to call that V sub 0 or V naught. So this is V naught or V sub 0. And then we need to know what angle it was launched. So, from horizontal, was it launched at a 45-degree angle, a 10-degree angle, an 80-degree angle? That's what theta is going to be. That's what this is. And that angle is from horizontal. So in calculus, if you go on to take calculus, you're going to see where this is derived from. You're going to see the derivation of this. For now, you kind of got to take my word for it. Basically, the x-coordinate of this projectile at any given moment in time is given by the initial velocity times the cosine of the angle times t, the parameter. So x is essentially the horizontal distance. So x is the horizontal distance from where it was launched. So that'd be the distance along the ground, if you want to think of it like that. And then y would be the height, right? So y is the height. It's the height above the ground at any given moment in time. So x is going to, so the parametrically defined x is initial velocity times cosine of the angle times the parameter. Now the parametrically defined y, or height, is -1/2 times g, talk about g in a sec, times the parameter squared plus the initial velocity times sine of the angle times t plus the initial height h. Now what is g? G is the acceleration of the object due to gravity. So we're on Earth, gravity is working on this object as it's in the air, and it's a constant force. So if things are measured in feet and seconds, time is in seconds and our distances are in feet, then g is 32 feet per second squared. If things are measured in meters and seconds, then g is 9.8. I think that's an approximation. They might both be approximations, I'm not sure. 9.8 meters per second squared. So pay attention to how your distances are being measured so you use the correct value of g. So with this setup, we can get the xy coordinate of the projectile in two-dimensional space at any given moment in time. So keep in mind, y would be height above the ground, and x would be the horizontal distance from where it was launched. So One of the popular sports here at Brebeuf is golf. Let's take a look at a golf example. So Sarah hits a golf ball with an initial velocity of 150 feet per second at an angle of 30 degrees from horizontal. So let's see what we can learn about this. So for example, we know that the horizontal distance from Sarah to the ball along the ground is going to be, well, the initial velocity, 150, times cosine of the angle that the ball was launched from, times the parameter t. So if we clean that up, that would be 75 square root 3 times t. Well, what about the height of the ball? Well, the height of the ball would be negative 1/2 g, but g is 32 because we're measured in feet. Distances are in feet, so it's going to be 32. Then t squared plus initial velocity times sine of the launch angle, t, plus the initial height. Well, playing golf, ball sitting on the ground, so the initial height's going to be 0. Initial height's going to be 0. So if we clean that up, make that look a little nicer, we're going to get negative 16t squared plus 75t. Now again, in calculus, you actually see where these two parametric equations come from, because it turns out you can start with the acceleration due to gravity and work backwards using the initial height and velocity to get this equation. And you'll see that fairly early on in a calc course. Well, one of the things we might be interested in is, when was the ball on the ground? Well, we know it starts on the ground, but when was it on the ground again? So, because if you knew where the ball landed, that's all kinds of great information. You know how far the ball was, how long it was in the air. So let's figure out when the ball was on the ground. So the ball is on the ground when its height is 0. Okay, well, so 0 would equal negative 16t squared plus 75t. That's a quadratic. You can just factor out t to solve it. And you're going to get t equals 0, but that makes sense because at the beginning, when t is 0, when time is 0, the ball's just sitting on the ground because Sarah hasn't hit the ball yet. But it's also on the ground 75/16 seconds later. So that tells me something. The ball is in the air for 75/16, which is about, maybe exactly 4.6875 seconds. So that's good information. I now know that Sarah hit the ball, and then 4.6875 seconds later, it hits the ground. So this is good stuff. That's useful information. Well, how far did it travel? What was the horizontal distance along the ground? So let's use my x equation for x, which is horizontal distance along the ground. So we know the ball was in the air for 4.6875 seconds, so let's plug that in for our time, our parameter time, and get the horizontal distance after that amount of time has elapsed. And that horizontal distance is going to be about, well, let's see here. If I do this right, 608.92 feet. So the ball traveled about 608.92 feet along the ground. Now, I know golf is usually done in yards, but you can convert to yards if you want. We're just going to stick with feet. Well, the other thing you might be interested in knowing is what was the max height? What was the highest the ball ever went? Now, remember, this defines its height, and notice it's quadratic. It's quadratic and opening downward, so finding its height is going to be fairly straightforward. So the max height, we just need to find the vertex of that quadratic. So there's lots of ways to find the vertex of a quadratic. You can complete the square. That's one option. That's the option I'm kind of a fan of. So if I complete the square here, do that real quick. So divide by 2 and square. Fractions are going to be a little, just a little annoying for a second, but we'll get decimals here in a sec. So divide by 2 squared, put that in there, adjust on the outside, and then in vertex form, go ahead and convert that to a decimal. I'm going to round that though. Then we get our max height. So I basically go right 75 over 32 and up 87.89 to get the vertex. So I now know the max height. So the max height of the ball is 87.89 feet. So again, we could find out some other stuff, but these would be kind of the main measurements you would want to know. How long was the ball in the air? How far did it go? What was its maximum height? These are all things that somebody might be interested in when they hit a golf ball. Okay, lastly, let's take a look at how you might start with a typical rectangular coordinate equation and convert it over to a parametric. So the example I've got picked out here is we're just going to do a parabola that opens upward. So I have y equals x squared minus 4. So it's got a vertical axis of symmetry. Matter of fact, it's just the parent function shifted down 4. But what if I wanted to define this parametrically? Well, one of the reasons we wait to do parametric equations is the same reason we wait to do trig functions with students. With trig functions, remember there are an infinite number of angles that share a terminal side on the unit circle, and that makes things kind of complicated. Well, if you take any given rectangular equation, I mean, there are just an uncountable number of ways that you could define it parametrically, which gets a little confusing. So we're just going to kind of play around with that idea real quick here at the end. So that's why I say find multiple ways to define the following parametrically. And there's lots of answers here. I'm just going to talk about a few of them just to give you a feel for what's going on. So for example, so what I want to do here is introduce a parameter, and I want my parametric equation to have the same graph as y equals x squared minus 4. I want this relation to be the same. I just want to define it parametrically. So option 1 is I could do it about arguably the easiest way possible. I could just let x be t. Then y would be t squared minus 4. So if x is t, then y would be t squared minus 4. Now let's see if this makes sense before we'll use the graphing calculator to verify whether this works or not. But let's think about it first. Notice the original is a second degree polynomial. So that means that x can be any real number, because polynomials have a domain of all real numbers. But it is the parent function shifted down 4, which means y has to be greater than or equal to 4. So y actually has a minimum of -4, but a maximum of infinity. It could go all the way up to infinity. So let's see if that'll be true with my option 1. Well, if I'm letting x be t, and I let t be any real number, then x could be any real number. So I'm thinking this is going to be just fine. Because if I let t be any real number, then x could be any real number, just like it was up here. And then any real number squared minus 4 would definitely be -4 or larger. So I think that's going to work. I think this is going to work. I'm going to give this the the early stamp of approval, but we're going to use the calculator to check. So I'm just going to hit Doc B to clear that out. Then we're going to go back to the graph screen, menu, graph entry, parametric. I'm going to let x be t. I'm going to let y be t squared minus 4. And then even though t could be technically any real number, I'm just going to pick a really wide interval just so it graphs a whole bunch of the curve so I can compare. And sure enough, that is exactly the parent function for x squared shifted down 4. So we're good. We're good. I like that option. But are there other options? Well, let's see. Do option 2. What if we let x equal t squared? Would that work? Well, then y would be, so x is t squared, so it'd be t squared squared minus 4. So y would be t to the 4th minus 4. Okay, well, let's try it. Let's try it. So Doc B, let's go to the graph screen. Let's go menu, graph entry, parametric. Let's go t squared. Oops, t squared. And then it would be t to the 4th minus 4. Ooh, uh-oh. I only got half the parabola. That's not good. Why is that? Well, actually, I see the problem right here. T squared is never negative. So x would never be negative. So we have a problem right here. X will never be negative. That's a problem because x originally was allowed to be any real number. So when I go to redefine it parametrically, I need to make sure the original domain and range are intact. And this would screw that up. By letting x be t squared, I'm saying x will never be a negative number, and that's not okay because it could have been negative. It could have been negative. So this right here is the problem. X will always be positive, but we want x to be any real number. So this doesn't work. This is no go. We can't have that. Well, what else could we do? All right. Well, let's learn from that mistake. So, option 3. What if I let x be t cubed? Ooh, now x could be negative numbers because we can get negative numbers out of t cubed. Then y would be t to the 6th minus 4, and I'm going to let t be any real number because then I can get, if t can be any real number, I'm going to get every possible value of x. So I think that's going to work. Let's see here. By the way, if you don't want to clear this, you can just hit Tab and go back up and edit it. If that's how you want to roll. Let's have that be to the 6 minus 4. Then let's go 20, negative 20. Ah, there we go. We get the whole thing. We get the whole thing. So remember, if we choose t squared, that doesn't work. You just get half the parabola. That doesn't work. So even though t goes from negative 20 to 20, like it's a big, nice, wide thing to graph, so I can see most of the graph, it still doesn't work because x is never going to come out to be a negative number. So that's a no-go. That's a no-go. So we found there's 2 ways to do it. Is there any more? Well, there's actually a lot more, and we can't go through all of them. Option 4, I could let x be t minus 3 because that would let x be positive or negatives. Then y would be t minus 3 squared minus 4. And again, I'd want to go ahead and let t be any real number, but I think that's going to work. Let's try it. If I let x be t minus 3. And then this would be t minus 3 squared. Yep. I think that's what we said. Let's double check. T minus 3. Yep. And sure enough, that's the parabola, x squared minus 4. So that worked out. So we got a few that worked. That worked. That worked. We got a few that worked. We found one that didn't, though. So I guess the main thing to get from this is that if you're going to define a given rectangular equation with a parametric equation, you got to make sure that the domain and range are kept intact when you redefine it. Otherwise, not so good.